Hi, grades of. Welcome to this session. It's an arithmetic and geometric sequences session where we're going to be focusing on some of the challenging questions such as divisible terms and recurring decimals, and also fractions and ratios. Okay, before wasting any time, let's just get to it. And it's the first challenging question about divisible terms. So the first one says, consider the sequence 1, 2, 3, 4 up until 1000. We know that 1 is our first term and 1000 is our last term because they show it is moving, then it's ending at 1000. So the first question says 1.1, determine the sum of the sequence. Okay, so before determining the sum of the sequence, we need to know what kind of sequence is that, right? So you can see 1, 2, 3, 4. Here we can clearly see the common difference is 1. So this is gonna be what? The sum of an arithmetic sequence. Okay. So we know the formula because we have our a and our last term. We're just gonna use the formula Sn equals to n over 2 a plus what? A plus last term. So we must get n, which is our number of terms. How many terms are we adding? So obviously from 1 up until 1000, there are what? There are 1000 terms, right? But you can actually prove it using Tn to say Tn is equals to what? When you use the common difference formula, when you use the general formula to get the Tn for that sequence, you're just gonna get n, right? So then your Tn, you put your last term 1000, then you will see indeed your number of terms is 1000. Okay, so we must also have a, that is our first term, it's 1. Last term is what? Our last term is 1000. So I'm just going to substitute on the formula. It's going to be 1000 over 2. Our a is 1. Our last term is what? Is 1000. Then use a calculator to get the answer. Okay, so the answer is going to be 500. So that's the sum of that sequence. 1.2, the question that I really want us to focus on, it says if the powers of 3 are removed from the sequence, find the sum of the remaining integers. So this is a bit tricky question, right? So where you have to find the sum with the restriction. So I call this solving arithmetic and geometric sequences with given restrictions. So now the restriction is that the powers of 3 are being removed from the sequence, right? So find the sum of the remaining what? Of the remaining integers. How can we do that? So to find the sum of the remaining integers, what we can do is we can get the sum of all terms, and we remove the sum of what? Sum of the powers of 3. So it's obvious that if we get the sum of all terms there and we subtract the sum of the powers of 3, we're gonna be left with the sum of the remaining what? Of the remaining integers. So we have already calculated the sum of all terms. Can you see in 1.1? Because we found the sum of all the terms in that sequence. So we already have the answer of that. It's 500 there. Then the sum of the powers of 3. You must know the powers of 3, right? So powers of 3, they have the base of 3 to the exponent n, where n is it's an element of a whole number. So it's powers of 3 is gonna be 3 exponent 0, right? The sequence 3 exponent 1, 3 exponent 2, 3 exponent 3, 3 exponent 4, like that going forth. Can you see? So we must determine their sum. But remember, from this sequence is starting from 1 up until 1000. So any power of 3 that will be greater than 1000, it won't fall under that sequence. So 3 exponent 3 exponent 0 is 1, 3 exponent 1 is 3, 3 exponent 2 9, 3 exponent 3 27, then 3 exponent 4, 81, then let's say 3 exponent 5, so 3 exponent 5, it will be 243, and 3 exponent 6, let me just add it on top, 3 exponent 6, so 3 exponent 6, it will be 729, right? Then 3 exponent what? 3 exponent 7, when you punch 3 exponent 7, look, 3 exponent 7 is giving me 2187. Can you see? So it's outside that sequence. Can you see? It's outside that sequence because the sequence is ending on 1000. It means 3 exponent 7, we won't include it. We just take from 3 exponent 0 to 3 exponent 6 because they are ending with a number that is included in the sequence. Can you see? So now we can go and get the answer. Sum of all terms, 500, 500. Sum of the powers of 3 is from 3 exponent 0 to 3 exponent 6. And we can see they are forming what? They are forming a geometric sequence because there's a common ratio there. If you take, let me just write them properly so that you can see and just to understand this. Okay, so, okay, here they. So you can see if you can try to calculate the common ratio here to say the second term divided by the previous term, you definitely get the same answer of 3 to show that there's a common ratio of 3. So to get their sum, you can either punch your calculator because these are small terms, right? Or you can just simply use a calculator, a formula to say, because these are sum of a geometric, the formula say a into r exponent n minus 1 over what? Over r minus 1. So you can go and substitute your value of a, r, and n, and you can just get the answer for that, right? So I'm just going to use the formula. So my value of a is 3 exponent 0. My value of r is 3. And the number of terms, let's count 1, 2, 3, 4, 5, 6, 7. Can you see? So don't make that mistake because here it's ending on 3 exponent 6 to say your number of terms are 6. So it's 7 because we also have 3 exponent 0. So the number of terms is 7. Then that's it, right? So I'm just going to say minus 1 over what? According to the formula 3 minus 1. Then we can get the answer for the sum there of the geometric series. So just gonna punch my calculator, get the answer. So the answer is going to be 1093. So that's the answer for the sum of the powers of 3, right? So to get the answer now, they said calculate the sum of the remaining integers if powers of 3 are being removed. We told you that to do this, you get the sum of all terms, then you subtract the sum of the powers of 3. So I'm just going to subtract the sum of the powers of 3, which is 1093, right? So it's 500 minus 1093, then the answer will give me 499407. So this will be the sum of the remaining integers, and that's basically how you approach this question. Okay. Let's now quickly look at a different example. Okay, problem 2 from this session, and this is about divisible terms, right? So the question goes like, given the arithmetic sequence minus 315 up until 393, they say calculate the sum of the terms in the arithmetic sequence that are divisible by 3, right? So here we can also call this series or calculating sums with given restrictions. So the restriction now here is to say you have to calculate the sum of those terms only that are divisible by what? By 3. So how do I know if a term is divisible by 3? Whenever you divide that term by 3, you don't get a remainder, right? So that's how you know. So in other words, when you divide it by 3, you just get a number or an integer, right? So an integer is any number from negative infinity to positive infinity. That is a whole number, sort of like such as minus 3 minus 2 0 1 2 3, like that. So you won't get an answer with a comma when you divide that thing by 3. Then you'll know that it's divisible by 3. So we have to calculate the sum of all the terms here that are divisible by what? By 3. So we must first go and draw out a sequence of terms that are divisible by 3. Okay, so minus 3 is the first one. We know minus 3 divided by 3, we're just going to get minus 1. There's no comma on its answer, so it's divisible by 3. 1 divided by 3, it's not possible, it's not divisible by 3. 5 divided by 3, it won't give us. Then we can just move with that sequence going further, right? So that we can have this sequence of terms that are divisible by what? That are divisible by 3. Okay, so what's the difference between the terms? They told us it's arithmetic, so 1 minus into minus 3 is going to give me 4. 5 minus 1 is 4. So to get the next term, I'm going to say 5 plus 4 is going to give me 9. To get the next term, it's going to be 9 plus 4. 9 plus 4 is going to give me 13. Then to get the next term, I can say 13 plus 4. 13 plus 4 is going to give me 17. Then to get the next term again, I'm just going to say 17 plus 4. And 17 plus 4 is going to give me 21. So we can just end up there and to say it's going up until 393. Okay, so we want to get the sum of the terms that are divisible by 3. Let's go and first draw out the terms that are divisible by 3 from this sequence. So the first one is minus 3 is divisible by 3. The other one is what? Is 9. It's also divisible by 3. And we know 21 also is also what? Divisible by 3. Now let's move towards the last term. Okay, so when we are moving towards the last term, we have 393, right? Can we check if 393 is divisible by 3? So I'm just going to say 393 divided by 3, and it's giving me an answer without a comma. So also 393 is divisible by 3. What if maybe I didn't have 393, maybe 392 here? So we would know that 392 is not divisible by 3. Then we'll just move backward up until we get the last term that is divisible by 3. How do we move backward? We subtract the common difference of 4. How do we move in front? We add the common difference of 4. Okay, so here we're just lucky we got 393, which is our last term, and it's divisible by 3. It's perfect. So now after drawing out a sequence of terms that are divisible by 3, it's going to be very easy to calculate their sum, right? Because we know they are forming what? They are also forming an arithmetic sequence. If you say 9 into minus 3, it's going to give you a difference of 12. If you say 21 minus 9, it's also giving you a difference of 12. So to get their sum, we're just going to use the sum of a what? Of an arithmetic sequence formula to say a plus last term, because we have the last term. So we must know how many number of terms do we have in this sequence, right? So to get the number of terms, we can use Tn equals to a plus n minus 1d. So our Tn is the last term, which is 393. Our a is our first term here, which is minus 3 plus n minus 1. The difference is 12. Just going to quickly do that and get the answer. So 393 plus 3 is going to be 396. 396 here. So if I just quickly divide also by 12, I'll be left with n minus 1. So 396 divided by 12 is going to give me 33. 33 plus 1 is going to give me my n, which is 34. So there are 34 terms in this sequence that are divisible by 3. Can you see? So, and how did we calculate them? We just draw out a sequence of terms that are divisible by 3. Then we just go and calculate our n. So I'm just going to substitute sum of 34 terms because it's only 34 terms that are divisible by 3. Then our a is minus 3. The last term here is 393. Now I can now get the what? The sum of terms that are divisible by 3. So just going to quickly do this on my calculator and see how much we can get. Okay. So when you patch a calculator, getting 6630. So 6630 is the sum of the terms that are divisible by what? By 3. Okay, so that's basically how you solve it. Let me just re-explain it again. What do you do in this case? you have to draw out, and you have to draw out the terms that are divisible by 3, because the instruction wants you to get the sum of terms that are divisible by 3. First step, you draw out the terms that are divisible by 3, get their number of terms, go and use sum formula and get their sum. Okay, let's move to a different problem. Okay, different problem. They are saying given the arithmetic series 2, 9, 16 plus up until we reach to 251 terms. So they are saying if all terms that are divisible by 4 are removed from the sequence, calculate the sum of the remaining terms. Calculate the sum of the remaining terms. So in order to solve this problem, you must know the sum of the terms that are divisible by 4, and you must also know the sum of all the terms, so that on the sum of all the terms, you're just going to subtract with the sum of terms that are divisible by 4, and you calculate the sum of the remaining terms. So that's basically how you approach this kind of questions with this kind of restriction. Okay, so what we're going to do is to get the sum of remaining terms, we say it's equals to what? The sum of all terms, then we remove, because they are removing the sum of terms divisible by what? Divisible by 4. So our duty really is to calculate the sum of all terms, then you subtract with the sum of terms that are divisible by 4. Now to get the sum of all terms, I'm just going to put it down here to say sum of all terms. Okay, so sum of all terms, we know this is an arithmetic series, and we're just going to use the formula Sn equals to n over 2, 2a plus n minus 1d. Then we have to know our number of terms, right? So they told you that this is up to 251 terms. It means that the total number of terms is what? Is 251. So our A is our first term, which is 2. Our common difference, let's go and get the difference there. You can just do it like this. 9 minus 2 is 7. 16 minus 9 is also 7. So the common difference is 7. Just substitute on my formula, sum of 251 terms, 251 over 2, 2 times 2 plus n, which is 251 minus 1, multiplied by the common difference of 7. Then I can just get the sum of all terms. Okay, just punch my calculator. I'm getting 220127 as the sum of all terms. Right, now I can quickly go and calculate what? The sum of terms that are divisible by what? That are divisible by 4. Now, before we get the sum of terms that are divisible by 4, you must know which sequence, what sequence is it forming, like the one that of terms that are divisible by 4. You must first remove the sequence of terms that are divisible by 4 from that original sequence you had, right? So our original sequence is 2 plus 9 plus 7, plus 16, plus if we add 7 as the common difference there, it will be plus 23. If we move further and we add 7 as the common difference, it will be 30. If we add 7 as the common difference, it will be 37. If we add 7 as the common difference, it will be 44. If we add 7 as the common difference, it will be 51, right? Going there towards there. Okay, so now sum of terms that are divisible by 4 is going to be quite tricky, but you'll understand it. So the first term that is divisible by 4 there is 16. Can you see? Okay, let's check with 30 whether 30 is divisible by 4. It's not divisible by 4. 44 divided by 4, perfect. 44 is allowing. So 44 is divisible by 4. Then we say plus 44, right? Let's quickly go and get maybe the last term that will be divisible by 4. Can you see? So here they told you that these terms are going towards, we reach 251 terms, right? but we don't know really what is term 251, so that this can also help us to get the last term this side. So to get term 51 from this sequence is going to be a plus what? Plus 250d, right? When you're going to use it from that formula, Tn equals to a plus n minus 1d. So a plus 250d. So what is my a? My a is 2. What is my common difference? My common difference is it was 7, right? So there's a little bit of background noise here. I'm really sorry about that. So it's gonna be 2 plus 250 into 7. Then my last term there, it will be 1752, right? So this is our last term on this sequence. Let's check whether this last term is divisible by 4. I'm just gonna divide it by 4. Perfect. It's divisible by 4. It's also part of our last term here. It's 1752. Can you see? So we are adding them up until then. So now we have constructed, or we have extracted, a sequence of terms that are divisible by what? That are divisible by 4. Okay, so now we can go and calculate the sum, right? So the formula for sum is Sn equals to n over 2. We can say a plus last term because we have the last term there, right? But we don't know the number of terms, right? How many terms are we adding from 1644 like that up until to 1752? So let's go and calculate the number of terms. Can you see there's quite a lot of things that we had to do? Hence this question will come roughly with plus or minus 7 marks, right? So let's go and calculate the number of terms. We use the formula Tn equals to a plus n minus 1d. Our Tn, we're just going to put our last term 1752. Our a is 16, right? Our a is 16. Remember, we are not using this sequence because here we are focusing on the sequence of terms that are divisible by 4. Hence, we are studying to add 16 because 16 is our first term that is divisible by 4 there. So it will be n minus 1. What is the difference here? 44 minus 16. 44 minus 16 is going to be 28, right? So my difference is 28. Just going to do that quickly. 1752 minus 16. Then quickly divide by 28 plus 1. And I'm getting 63. And I'm getting 63. To show that there's only 63 terms from this sequence that are divisible by 4. So where there is n, I'm just going to put 63. It's going to be 63 over 2. What is my a? 16. What is my last term? 1752. Then I can get the sum of terms that are divisible by what? That are divisible by 4. Okay, so let me just do this quickly. 63 over 2 into 16 plus 1752. Then I'm getting the answer of 55692. So this is the sum of the terms that are divisible by 4, right? Let me just write it in red now as we go towards the final answer. The question says calculate the sum of the remaining terms. So we first started by calculating the sum of all terms, which is 220127. We have to subtract the sum of terms that are divisible by 4. We calculated it. It's 55692. Then we can get what? We can get the final answer, 220127 minus 55692. So the final answer will be 164435. Okay, so this will be the final answer for the sum of the remaining terms. So now here the challenge is maybe you getting the sequence, extracting a sequence from this sequence of the terms that will be divisible by 4. But I don't really think it's a challenge. You just need to check the terms that are divisible by 4. How do? You just expand that sequence a little bit, just as I did. Then you identify those terms that are divisible by 4. Then you form a sequence there. Then you can go and calculate. Okay, let's now move to different challenging questions on series, and this is recurring decimals, trying to express them as fraction. There is a standard approach to this kind of equation. So the question says express the following in terms of fractions. Hint, use your knowledge of sequences and series, right? So we're just going to use our knowledge about sequences and series in order to express the following decimals recurring decimals in terms of a fraction. So A, you are given 0.33333, and we can see this is going to infinity. Can you see? It's recurring towards infinity. You must think of sum of what? Of infinity. So sometimes they'll just give you as 0.3, then they put that dot on top to show that it's recurring. So you have to use your knowledge about sum to infinity now. How do we do that? You rewrite this decimal as a series, and you know sum to infinity is of a geometric series. So what you do, you rewrite it as a geometric series, sort of like. So 0.3333, how we're gonna do it? It's gonna be 0.3 plus what? 0, so that it can be 0.33, it will be 0.03. Can you see? So it must be 0.03, so that when we say 0.3 plus 0.03, it's 0.33. Then as we move, you just say 0.00. You make those numbers 00 now, 003, right? So that it can make sense. We go further, it's going to be 0.0003, like that. And we know it's going to infinity, so that it can be 0.3333, like that. Okay, so now we can see we have a geometric series. We can calculate its sum. Its sum to what? Its sum to infinity, this one. So we have our A over 1 minus R, and this is our formula. What is our A? Our A is our first term, which is 0.3. What is our R? Our R is the common ratio. And how do we get common ratio? You said this second term divided by the previous term. Then this is just going to give you, I think, 0.1. So you put your R is 0.1. You can punch your calculator and simply express that thing in terms of a fraction. When I punch my calculator, I'm getting 1 over 3. So you can also prove is 1 over 3 0.3333. You use your calculator, you press 1 over 3, then it will definitely show you 0.33333 to infinity, like that. So that's basically how you do it in all these problems. So B, C, and D are just some different ways in which you can do this, and there are some of the challenging questions. Let me just show you quickly, then we move to some of our last problems. Okay, for B, you are given 1,22222 recurring. So what you do in this case, in order to rewrite it as a fraction, you must first write it as a series, right? So the only thing that forms part of your series is those things that are recurring, right? So the rest of the things, they don't really form part of the series. What do I mean? So when I rewrite it, it's going to be 1 plus. If I remove 1, I'll be left with 0.2222 recurring, right? Because 1 is not recurring. I just want to express this as a series because they are the one that can be expressible in that sense. So then it's 1 plus, if I express this, it's going to be 0.2 plus what? 0.02 plus what? 0.002 plus what? 0.0002, like that, going towards infinity. Can you see? So then it's going to be 1 plus, here we can get the sum to infinity, 0.2 as our A, 1 minus, what is our R? You take 0.02 divided by 0.2, it's giving me 1 over 10, which is 0.1, right? So I'm just going to punch a calculator and get the answer for that. For the sum, 0.2 over 1 minus 0.1, it's going to give me 2 over 9. So the final answer will be 1 plus 2 over 9, then it will give me 11 over 9. And we have expressed this as a what? As a fraction here. And we can prove whether 11 over 9 is going to give us 1,22222. So when you punch your calculator 11 over 9, it should give you 1,222 to show that you have done correctly. Okay, let's move to C. Okay, with C, we are given 2,13131313. Can you see that 131313 is the ones that are recurring? So this one is a little bit challenging, but you do it using the same approach to say you take 2 out there, then you'll be left with 0,13131313, like that, going towards infinity. Can you see? So after doing that, we can write this one in brackets in terms of a what? In terms of a series, to say 0,13. Can you see? Plus what? 0, you made these zeros now. 0,00, then you can say 13, right? So that it can make sense when you add up those. So also here we say 0,0000, it will be 4 zeros this side, and you say 13, and this is added going to infinity, right? So we can get the answer. Remember, in brackets is sum to infinity, and sum to infinity is a over 1 minus r. Our a is 0,13. What is our r? So to get your r, you take the following term and you divide it by the previous term. So it's just going to be 0,0013 divided by 0,13 is giving me 0,01, right? So I'm just going to punch a calculator to get the answer for that. 0,13 over 1 minus 0,01 is giving me 13 over 99, right? Then I'm just going to add that with what? With 2, then it's giving me 211 over 99. So in other words, if you are to express this one in terms of a fraction, it must be 211 over 99. And when you punch it on your calculator, it should give you this decimal to say 2,13131313 like that. Okay, let's quickly go to the last one, D. Okay, D, it's 1,45 recurring. So this is a little bit challenging, but we know we can write this as 1,4. The number that is recurring is only 5. Can you see? 5, 5, 5, 5. And we can see it going towards infinity like that. So if we have to rewrite it, remember we write as a series those ones that are recurring. So 1,4 will just be outside. Then to write those ones that are recurring, this one here is going to be 0, this 4 also it will be 0, right? 0 what? 5. So that when you add them up, they still give you 1,45. Then plus this one will be 0,005 plus 0,0005, like that, going towards infinity, right? So we can go and get the answer for this inside the bracket. Our a is 0,05 over 1 minus, what is our r? We take 0,005 divided by 0,05. It's just going to give me 0,1. So my r is 0,1 there. I'm just using the sum to infinity formula to get the answer for that, right? So that we can express it as a fraction, 1 minus 0,1. Then this will give me 1 over 18. So 1,4 plus 1 over 18, just going to give me 131 over 90. So if you punch 131 over 90, it's just going to give you 1,4555 to show that really, if we are expressing this as a fraction, this must be its fraction. Okay, let's look at this other challenging question. What value does 2 over 5 to the exponent of n approach as n tends towards infinity? Can you see this symbol of infinity? So they want you to know what value does 2 over 5 exponent n approaches as n tends towards what? Infinity. So it's simple. They simply want sum to infinity. So you have to calculate sum to infinity to be able to know what value that this approach as n tends to infinity, because our n is now going towards what? Infinity. Can you see? So in that case, we are just going to use a formula of sum to infinity, a over 1 minus r. What is our a? Our a is our first term, so it will be when n is equals to 1, right? So it will remain 2 over 5. What is our r? Our r is determined by the second term divided by the previous term. So our second term will be 2 over 5 squared. Our first term is 2 over 5 exponent 1. This will just give us 2 over 5. Also as our what? As our r. Go and substitute 2 over 5 as our a. 1 minus our r is also what? 2 over 5. So just gonna substitute that and just get the answer, right? So 1 minus 2 over 5 like that on my calculator, I'm getting 2 over 3. So you can see what value does 2 over 5 exponent n approaches as n towards infinity. It approaches what? 2 over 3. So it approaches 2 over 3, and it was just a tricky question that was asking you to calculate sum to infinity in this tricky way. Okay, let's take a look at our last problem, and this one is focusing on ratios, right? One of our last challenging question on sequences and series. So it says the first term of a geometric sequence is 9. So we have our A is equals to 9, and the ratio of the sum of the first 8 terms, to the sum of the first 4 terms, is 97:81, right? So they gave us the ratio there. They say find the first 3 terms of the sequence if it is given that all the terms are positive. Okay, so they want us to get the first 3 terms of the sequence. We only know the value of A, which is 9. How can we do that? So that ratio, we can write it actually as a fraction. Sorry about that. To say sum of 8 over sum of 4 is going to be equals to 97/81, right? So we know the formula for calculating sum of a geometric series because they told us this is a geometric. It's A into R exponent n over what? 1 R minus 1, like that. So our A is 9. I'm just going to put 9. R, I put it as R because we already have it. N number of terms is 8 minus 1 over R minus 1. So this is the first one on top. Then we go to the sum of the first 4 terms. Our A is 9. Our R remains R. Our N is 4 minus 1 over R minus 1. So this will be equated to what? To the ratio 97 over what? Over 81. Can you see? So R minus 1, R minus 1 will cancel out each other. 9 and 9 will also cancel out each other. Then we'll just be left with R exponent 8 minus 1 over R exponent 4 minus 1 is equals to 97 over what? Over 81. Then we can just simply cross multiply. So 81 will multiply with R exponent 8 minus 1. Then 97 will multiply with R exponent 4 minus 1. So it will be 81 R exponent 8 minus 81 when we remove by 81. That side will be 97 R exponent 4 minus 97. Then we can just simply take this to the other side. They will just change their sign to be 81 R exponent 8 minus 81 minus 97 R exponent 4 plus what? Plus 97. Then we'll be left with 0 that side. So if I can write it properly, it's 81 R exponent 4 minus 97 R exponent 4 minus 81 plus 97. So it's minus 81 plus 97. It's going to give me plus 16 is equals to 0. So can you see now, this is R exponent 8, sorry. So can you see now that this one, we can use the K method to say, let K be equals to R exponent 4. Or you can basically factorize this, right? If you know how to factorize. So when you factorize, it's going to be, so it's going to be 81 R exponent 4. Let me check. 81 R exponent 4 plus, is it going to be plus? I think it's going to be minus 16. Then this side, it will be R exponent 4 minus 1. So that's how it's going to be when you factorize. Or you can simply use the K method. It's just that the K method is long. When you say let R exponent 4 equals to K, then you rewrite it in terms of K, then you go and solve for R. It's just going to be a long method that way. Let me write in, oh, I'm sorry about that. The weather just changed here, so it's a little bit noisy on my background. Sorry about that. So when I solve for R there, it's going to be 81 R exponent 4 minus 16 being equated to 0. Or R exponent 4 being equated to 1. So 81 R exponent 4, it will be equals to 16. to solve for r, divide both sides by 81. This one cancel out this one, then I'll be left with r exponent 4 equals to 16 over 81. To cancel that, I'll apply the fourth root. When you apply the fourth root and the square root, any root of a number divisible by 2 or of an even number has to have plus or minus, right? So r will be plus or minus the fourth root. Remember, this is the fourth root of what? Of 16 over 81. So this is gonna give me 2 over 3. R is 2 over 3. Then here, when we apply also the fourth root, because we are applying a fourth root, the 4 is an even number, so r will be plus or minus 1. So we have the two r's. We can now go and get the first three terms, right? So our a is 9, so it will be 9. If we multiply with, remember they say for positive terms, for all positive, so we'll consider r that is positive. If I say 9 times 2 over 3, 9 times 2 over 3 as my r, it's gonna give me 6. So it's gonna be 9, 6 times 2 over 3 again is gonna give me 4. So this is the first three terms. So we also have another one for 1, right, where r is equals to 1. So this is when r was equals to 2 over 3. So when r was equals to 1, the sequence will say 9. 9 times 1 will remain 9. 9 times 1 will remain 9. So we have those two positive sequences that will be formed. If we are considering r that is positive. Okay, good stuff. This marks the end of our session. Thank you very much for watching. Thank you very much for joining. If you're new to this channel, just make sure that you have subscribed and hit the notification bell so that you may get notified every time when we upload these new sessions. Otherwise, if you enjoyed the session, if you learned something new, just hit the thumbs up there and just drop your comment and let us see how we can improve our sessions going further. Otherwise, that's all for me. Thank you very much for watching and goodbye.